Okay, so now let's get it started. So the problem five. Okay, so our problem five is asking us to find the location of the centroid and the moment inertia radius of gyration of the composite shape here. So clearly the composite shape is composed of two triangles, and we are required to first find out the location of the centroid, and then they determine the moment of inertia and radius of gyration of the composite shape. So the problem actually is guiding us by first to solve the location of the centroid, and then we can go ahead and evaluate the moment inertia and the radius of gyration about actually the the axis x prime and y prime that crossing the centroid of the shape. Okay, so how are we going to approach that? Okay, give me 1 second. Okay, so how are we going to approach that? Well, first, so what are the four formulas that we are going to use to find out the location of the centroid here? Okay, so please recall the the four formula that we were going to use. Okay, so at least so we know that the centroid for a composite area is actually it is a weighted average of the centroid of each part, right? Actually, it is a each regular shape. So it is a summation of the area I and centroid I divided by the total area, right? Okay, so now by seeing that we have the summation over several areas that denoted by I here, we mean that we are going to divide the composite we are going to divide the composite shape into into regular parts. So if we look at this shape here, so it can be divided into two parts, right? So it can be divided into two triangles actually here, right? So it is a triangle one and a triangle two here. Okay, so now we can see that so the I is actually from one to two, and we are going to take so we are going to plug in the area and the location of the centroid of each part into the formula here, right? Okay, so now let's go ahead to do it. And first we have the numerator here. So the new numerator here, and for the it is the summation of area times the location of actually it is the coordinate of the centroid here. So the area of the first triangle here equals to it is actually a half of the base, and the length of base is specified by there's 20 here, right? Okay, times base 20 and then times height, right? And it is again 20 here. Okay, and then times the location of the centroid of this big triangle here, which is located at okay. So now actually you can so for both the formula to calculate the centroid and the location of the standardized actually regular shapes, you can go to the appendix. You can go to appendix of the exam. Okay. It is so for the formula of sense so for the formula of central or in other words it is the centroidal coordinates of area. So we have it here. Okay. And it is for composite area if you see that it is a summation because it is for discrete form. Okay. And for our triangle here, so we can see that the location of x prime, right? The location of x prime, its the distance from the side equals to what? Okay, its distance from the sides that are parallel to the x prime uh axis is actually 1/3 of the head, right? Okay, okay. So actually, it is a one third of the head, or it is a distance that's perpendicular to the to the x-axis. Okay, okay. So then, if we go back to the original triangle here, okay, for the triangle one, then where is my x coordinate of the centroid of the first part? So we know that. So if we denote the centroid of the first triangle here, the distance, okay, the distance from the centroid to the head equals to 1/3 of the base, right? It is a it is 20 divided by 3. Then the distance from the origin to okay, then the distance from the origin will be 20 minus that distance here, right? Okay, that is actually the centroidal x coordinate of the first part. Okay, it is 20 minus 20 divided by 3. Okay, so similarly for the second part. Okay, so first we have area. It is 1/2 times the length of base, which equals to 30 minus 20 here. Is actually 10. And the head, it is the same as the first triangle, it is 20. And then times the location of the centroid, right? And where is it? Okay, again, we find its coordinate by first to find its distance from the centroid to its head, which equals to again 1/3 of the base, and the base actually equals to 10, and 1/3 of the base is 10/3, right? And then its x coordinate equals to this distance plus okay the location of the head, right? Which is actually at 20 here. So the central x coordinate uh of my second part is actually 20 plus 10/3. Okay. And then this is the numerator. We divide it by the total area, right? So it is the area of the first part plus the area of the second part. Okay. So now you can go ahead to evaluate that. It actually equals to, okay. So we have a numerator equals to 20 times 20 divided by 2 and times 20 minus 20 divided by 3. Okay. Plus 10 times 20 divided by 2, it is the area, times the central x coordinate of the triangle, which equals 20 plus 10 divided by 3, right? Okay, we have 5,000 here. Okay, so the denominator here equals to a half of 20 times 20 plus a half. times a half times 10 times 20 here is 300. And that actually gives us, okay, please ensure to include the correct unit here. Well, does that looks make sense here? Well, if you so you see that it is slightly smaller than 20 here, right? So it makes sense, right? Because it should be at roughly at the very roughly at the middle of the ship, right? So now we have y bar can be similarly calculated. So we have everything to be the same. It is again the we it is a weighted average, right? But we now replace x with y. Okay. So we're gonna have again area a half of the base times height, and now times the y coordinate of the first of the centroid of the first shape, we which is actually, so as we know that, so the distance from from the centroid of the triangle to its base equals to equals to one third of the height, which is 20 over 3, right? Okay, so that is actually also the y coordinate of my of the centroid of the first shape. So we have 20 over 3. Okay, so how about my second part? So for my second part, it is 1 over 2 times 10 times 20. Okay, then times again the distance from my centroid to base or to the x-axis is my y coordinate here, which is actually equals to, again, one third of the head. It is 20 divided by 3. Probably now you already know the answer here, right? Okay, so another idea to approach that is that you can take the composite shape as a big triangle. And you know that for the big triangle, the distance from the from its centroid to the x-axis is actually equals to one third of the head, and head is actually also a distance that's perpendicular to x-axis, right? Okay, so it's divided by the total area, right? And we're gonna have it to be, so we know that it will directly be 20 over 3 millimeter here, which actually equals to, okay, 6.67. Okay, so this is actually the answer for the first part. It is actually the location of the centroid here, which is 16.67 and 6.67. And the unit here is a millimeter here. Okay, so this is the first question here. And then we can proceed to the second question here. So the second question, so the second question here is actually asking us to determine the moment of inertia or the radius of gyration of the composite ship. Okay, so how can we approach that? Now it is actually here we are trying to find the moment inertia of the composite area, right? We are trying to find the moment inertia of the composite area. Okay, so the moment inertia of a composite area about an axis, how can we approach that? So always, and for the contents that we covered at the last one third of our semester, it is always important to be realized what is a correct formula to use here. So here we are supposed to find the moment inertia of an area about an axis, right? So okay, so we should have okay, so that will require us to use parallel X theorem, right? Parallel X theorem. So by parallel X theorem, we know that the actually it is a moment inertia about an axis equals to the summation of the centroidal mass moment. It is a centroidal moment of moment inertia about actually it is of each part, right? Plus the area times the square of the distance. It is the distance between the centroid of each part to and the axis that we are going to evaluate in the moment inertia here. So now actually it is actually the centroid of the entire composite area, right? Okay. So now we can go ahead to evaluate that. So so first, if we go to the area one, okay. So the central moment inertia of the area one equals two. So it is a triangle, and if we go to the appendix, if we go to the appendix here, we see that okay. So the central moment inertia about x prime is actually 36 times b h to the power 3. Please note that the reason why h is to the power 3 is h is perpendicular to x prime here. And for for our case, okay, so we are evaluating the central moment inertia about y-axis, right? About y-axis. Therefore, they uh actually they decide that perpendicular to y-axis is actually the quantity here, right? It is the base. So we're going to have the moment inertia of the area one equals to 1/32 times okay times the sides that's parallel to y-axis we which equals to 20, and the sides that perpendicular to y-axis again it is 20, but for the sides that perpendicular to y-axis, so it is 20 to the power of 3, right? Okay, and then plus the area 1/2 times 20 20 here, and then times the distance between the centroid of the area one and the centroid of the entire shape. So it will be actually it will be the distance, it will be the difference between the centroid of the area one and the total area. So the centroid of area one, we will already have that in the first part, right? So it is actually here. So it's 20 minus 20/3. Okay. and then minus. Okay, so now we need to subtract the coordinate of the centroid of the entire area, which is actually 16.67. Okay, so this is the reason why the problem asks us to first find out the location of the centroid of the entire area, and then square of that. Okay, this is actually the moment inertia of the area 1 about y prime here. So plus what? We're also going to include the moment of area of the moment of the inertia of the second area, right? So again, it is a 1 over 32 times, okay, now times first it is the length of the side that parallel to y prime, right? So it is actually 20. And then times the uh length of the side that's perpendicular to y, or the head that perpendicular to y, which is actually 10, right? So it is 10. Okay, plus 1 over 2. Okay, so times the actually it is the product of the two sides, right? It is the area of the triangle. Then times, okay, now it is a difference between the uh between the x coordinate of the area of the centroid of area 2 and the x coordinate of the entire area. Okay, the x coordinate of the centroid of the second area is we've already have that in our first part, right? So it is 20 plus 10 over 3. Okay, minus 16.67 and square of that. Okay, so this so in the second line here is the mass moment inertia. Oh, sorry, it is a moment inertia of the area 2 about y prime axis. Now you take the summation, you can evaluate that. Okay, so it actually equals to the first part is 6671. Okay, the second part is 4996. Okay, so we are gonna have it equals to, so it is 11,667. Okay, so be sure to include the unit here, and the unit for moment inertia is the length to the power 4, right? So it is millimeter here to the power 4 here. And we also require to find out the radius of gyration, right? Radius of gyration, how we can find that? It is a square root of right? It is square root of the moment inertia divided by area, right? We have that in the previous question as well. So for the moment inertia, we already have that, right? Okay. And for the area, right, it is a total area, which is actually the summation of the area of each part, right? Okay, and then you take the square root of that, which actually equals to. Okay. So now you have the square root of that divided by. Okay, so it is a square root of the moment inertia and divided by the total area, right? Okay. And we've already also have the total area in the first part as well. And if you evaluate that, you are going to see that it's equals to 6.24, right? And the unit here should be millimeter, right? Okay, so now it is actually the answer for the second part. Be sure to include the correct unit here. Okay, so now this is actually for the problem 5 here. So the problem 5 evaluating it is examining us if we can calculate the location of centroid moment inertia and radius of gyration of a composite area. So please note here that for the location of the centroid, it is actually a weighted sum of the centroid of each part. So we need to divide the composite area into several regular shapes, and then we know that location of centroid is actually the weighted average of the centroid of each part. So for the moment inertia here, it is a k, right? Because compared with the moment inertia, the calculation of radius of gyration is more straightforward. So the moment inertia, to evaluate that, we need to use parallel x theorem. Parallel x theorem, it is crucially important here. So to calculate the moment of inertia of each part about an axis that we want to evaluate that, and then we can take the summation of the moment inertia of each part, right? And so when we are applying parallel x theorem, it also requires us to evaluate the central moment inertia of each part. So that is given in the appendix. But of course, so even we have the appendix, we need to take a practice to ensure that we can make use of that. Although the information is there, we need to know what does it mean. Okay,